Welcome back to the series. Today, we're stepping back from GPR itself to see how it fits into the larger world of subsurface investigation. Now, whether you're tracing buried pipes or cables, inspecting bridges, mapping geology, or studying glaciers, you always have choices. GPR is just one tool that geophysics offers. It is powerful, but it's not magic, and it isn't always the right tool at all. So, in this episode, we'll explore when radar excels and where it struggles, and how it complements other techniques like EM locating, or electrical resistivity tomography, or seismic, ultrasound, or deeper EM tools. And by the end, I hope you'll have a clearer picture of when to reach for that GPR and when to try something else or call on a geophysicist for help. If GPR has a household reputation anywhere, it's in utility detection. The task is deceptively simple, right? Find pipes and cables beneath streets and construction sites and do it accurately enough that nobody hits anything when they dig. GPR shares that stage with electromagnetic locating, acoustic leak tracing, tracer gas methods, thermal cameras for heating pipes, and a handful of other niche tools. Each of these sees the underground very differently. EM locating is a veteran workhorse for metallic utilities. You'll call it radio detection in some places, but it's all the same concept. The idea is to induce a current into a conductive line, a metal pipe or electric cable, and then follow the magnetic field that the current produces. It's fast, it's proven, and it's beautifully effective when the target conducts electricity. The catch is in the physics. If it doesn't conduct electricity, it just doesn't respond. So like plastics, PVC, HDPE, concrete, and clay pipes are invisible to EML surveying unless somebody had the foresight to install a tracer wire. That's where GPR fills in the blind spots. Radar reflects from contrast in dielectric properties. That means it can pick up non-metallic utilities directly, and in many cases it reveals the trench where the utility was laid in, the disturbed soil that lingers as evidence of past construction. Acoustic methods bring a different advantage. By introducing vibration or sound into a pressurized line and listening with surface sensors, they can follow a continuous pipe and even pinpoint leaks, even in places where radar penetration completely doesn't work, like saturated clays, saline fill, or very noisy urban environments. The trade-off is access and conditions. You usually need to connect to the system, and a water-filled pipe is where the approach really shines. Tracer gases and thermal cameras are specialists, excellent for confirming leaks and showing heat losses, but not for mapping entire networks on their own. So, where does that leave GPR? In a very useful middle ground. Radar can detect both metallic and non-metallic pipes and cables. It can estimate depths, and it can reveal nearby features, voids, disturbed soil that other methods simply can't see. But its limits are also clear. Conductive soils, especially clays or saline backfills, they soak up radar energy and they cap the depth you can reach. Congested sites demand careful survey geometry and interpretation, and accurate depths depend on realistic velocity calibration on your GPR datasets. In practice, the best workflow isn't choosing just one technique over another, but by using them in pairs. So use EM locating to trace conductors, use GPR to pick up the non-conductors, and to visualize trenching and add context, and to cross-check between the two. Think of them as partners and not competitors. Let's move from soil to structure. In civil and structural engineering, GPR is a mainstay for scanning slabs, bridges, and walls. Here, radar answers a very specific set of questions. What's inside? Where is it? And how deep is it? High-frequency antennas resolve rebar, post-tension cables, conduits, voids, delamination with centimeter scale detail. Now, because steel and air contrast really well with concrete, reinforcement bars appear very bright and crisp, while air-filled voids feature Often, those features show the telltale polarity flip that a trained eye will recognize. But radar is not a strength test at all. It's simply an imaging method. When engineers need to judge material quality or estimate compressive strength, they bring in different tools. The Schmidt hammer, for example, provides quick, inexpensive assessment of surface hardness that can be loosely correlated with strength. It's a shallow tool and it's sensitive to surface conditions, but it's useful for screening. Ultrasonic pulse velocity pushes sound through the concrete, similar to radar, but using sound waves, and times how long it takes to come back. So just like a two-way travel time like a GPR. Now it's sensitive to cracking and voids and stiffness, so it's excellent for integrity tests or to look at water-saturated elements where the radar might struggle. But it produces travel times and velocities, not a picture of the subsurface. So, in practice, a good concrete assessment blends the methods. GPR maps the geometry, where the rebar is, how the slab is built, where delimitation might exist, and ultrasound or rebound testing fills in the material story. Together, they provide the what and where and the how sound it is, reducing invasive coring and focusing repairs where they are actually needed. Let's talk about pavements. Out on the road network, GPR has become a standard non-destructive test. Vehicle-mounted systems can scan at highway speeds using horn antennas, and they build continuous images of pavement layers. Agencies around the world use these surveys to estimate thickness, to spot moisture ingress, and to flag voids and debonding before they turn into failures and potholes. Now, because the dielectric constant correlates with moisture and the material type, radar is super sensitive to wet zones and layer changes that mechanical tests can miss. So, of course, it doesn't replace everything. Falling weight deflectometers remain the tool of choice for measuring how pavement responds to load and for back calculating stiffness and, I guess, the remaining life of the pavement. Coring is still a definitive check for exact materials and binder content, but it's invasive and slow, so radar helps decide where to core rather than trying to replace it altogether. Embedded moisture or resistivity probes offer continuous readings, but only at isolated points. Radar fills in the space between those points. On railways, the story is pretty similar. GPR can roll along the track identifying ballast fouling. That fine material comes from a lot of, well, industrial use, but it's also coal dust and coal tracks that chokes drainage and reduces stability over long distances with remarkable efficiency. But the limitations show up when the ballast is saturated or highly conductive. The penetration fails, and the contrast between clean and fouled ballast is really difficult. So other tools, usually, well, material sampling, step in to quantify compaction and drainage properties. The value of radar in these networks is speed and coverage. It paints the big picture so targeted tests can dig into the details of where radar sees anomalies. Now let's zoom out and talk about geological and environmental work, where GPR shares the stage with a much broader cast of electrical resistivity tomography, magnetometry, seismic methods, transient EM, and fixed frequency EM, passive seismic, a whole host in the geophysicist toolbox. Each of these relies on different physics, which means that each excels in different ground conditions and in different depths. Geological mapping is the domain of actual geophysicists who will know all of this information anyway. But I thought I'd include it here just to give context to GPR users. Electrical resistivity tomography, or ERT, sends current into the ground and measures the resulting voltage field to reconstruct a subsurface resistivity pseudo-section. It's amazing at imaging moisture contrast, clay zones, and contamination plumes, things that vary primarily with electrical conductivity. It also penetrates far deeper than GPR, often tens to even hundreds of meters, and it keeps working in conductive soils where radar absolutely dies. The trade-off is acquisition speed and resolution. ERT grids take a long time to deploy and measure, and the resulting images tend to be smooth with less sensitivity, small, sharp targets. So it's useful where GPR doesn't work. Magnetometry measures tiny variations in the Earth's magnetic field caused by ferrous material or magnetic materials. It's a go-to tool for archaeology and unexploded ordnance, and it can map large areas rapidly in conditions that eat up radar signals, wet clays, for example. But it's blind to non-magnetic materials, plastic, wood, and many stones, and those materials leave no magnetic signature at all. What's interesting, though, for archaeology is that burnt materials, so anything from fire hearths to brick, turn up quite nicely on magnetic surveys. Seismic methods, refraction and reflection surveys, use sound waves to profile the subsurface. They can see very deep and are excellent for bedrock profiling, void detection, and estimating mechanical properties through velocity contrasts. Seismic requires good ground coupling and access for sources and sensors. And while its resolution near the surface is improving, it generally can't match what radar can do because we're at centimeter scale for the shallowest layers. But seismic can go to tremendous depths, kilometers deep if needed. Transient EM systems and fixed frequency EM induction are conductivity mappers. TEM measures the subsurface response to a decaying magnetic field and can reach very impressive depths, sometimes hundreds or even kilometers deep with a large enough loop. While instruments like the EM31 and EM38, these are fixed frequency EM systems, provide continuous near-surface conductivity measurements as you walk along or tow it behind a vehicle. And these are fantastic for salinity surveys, groundwater and contamination surveys. But they and what they produce is essentially a near-surface conductivity model, but not images of discrete objects. If GPR gives you a high-resolution photograph of the shallow layers and targets, EM gives you like a heat map of conductivity variations. It's complementary, but they're very, very different tools and they give you different information. So, well, where do you choose which one's which? Well, if you're looking at geological surveys, that's the domain of a geophysicist. And that's what we study for years and years. So we know which tools to use. And quite often, GPR is not it. So you reach for your GPR when your targets are shallow and you need high resolution to look for buried targets, soil stratigraphy, sinkholes, archaeology, concrete, pavement, ballast, anywhere detail matters and the ground isn't too conductive, electrically conductive. You would choose ERT or EM methods when you need to see deeper or where clay or salinity absolutely kill our radar signals. We would use seismic when mechanical properties or bedrock architecture or much deeper horizons are the priority. And we would, of course, bring out magnetometry and EM induction for metallic or magnetic anomalies over large areas. None of these tools are better in absolute terms. Each one answers a different version of the question. Few applications show GPR strengths more clearly than glaciology. Radar waves travel through ice with very low attenuation, almost like light through clear glass. And the contrasts at the ice to bedrock interface or ice to water boundaries are very strong. That combination gives you deep penetration and excellent resolution at the same time. So it's no surprise GPR has mapped ice sheets in Greenland and Antarctica, profiled mountain glaciers, and even probed polar ice caps on other worlds for almost 100 years. So other methods have their place. Seismic surveys can measure ice thickness and the bedrock beneath, but they demand sources, explosives, or heavy hammers, and they struggle with coupling on hard frozen surfaces. Boreholes and ice cores deliver exquisite detail, but only at single points, and they come with heavy logistics. Satellite radar altimetry gives continent scale elevation changes, but not much internal layering. At best, satellite radar can penetrate tens of centimeters into the ground. So GPR sits at the sweet spot of fast, non-invasive, continuous, and detail, right? It's able to show thickness, internal stratigraphy within ice, and even zones where liquid water lurks within or beneath the ice. For understanding flow, mass balance, and climate signals, archived in those layers, it's hard to beat GPR. Every subsurface investigation begins with a question, and every question has a physics best suited to answer it. GPR's strength lies in high resolution imaging of the shallow subsurface without digging. Its weakness is in conductivity, in clay rich, saline, or water saturated soils. The signal fades before it can paint the full picture. Electrical resistivity, seismic, magnetics, acoustic methods each offer windows into the underground, sometimes trading resolution for depth or speed for specificity or images for property estimates. The most reliable answers come from a concert of methods, putting them all together in a symphony. Use radar to sketch the fine detail, then lean on electrical or seismic or EM to carry out the story deeper. Use magnetometry to find ferromagnetic materials or old burn pits or where archaeological sites are, and radar to tell you where they sit exactly within those layers with depth. Use high-speed GPR to scan at railway speed or highway or railway speeds along corridors, and then send in coring deflectometers or targeted samples to see what the image to confirm what the GPR is saying and to follow up on anomalies. The art isn't in declaring a winner, it's in matching the tool to the task and the ground you're looking for. So often with GPR, we see that companies only have GPR systems, and then it becomes a case of for every problem, if all you have is a hammer, then every problem becomes a nail. And that is literally what the field of geophysics is. There's a geophysicist on LinkedIn that you can write to, and they'll be happy to tell you that GPR might not be the right tool for your application. And that's where you need to phone a friend. So when somebody asks, is GPR the right tool? The honest answer is, well, it depends on what you're looking for and what you're looking through. That's the heart of geophysics, choosing the right physics to illuminate the truth at the right scale for the question at hand. Thanks so much. I'll see you on the next episode.